Okay, welcome back. In this video, I'm going to introduce how to construct Artzt parabola using projective space. Let's first take a look at the very simple demonstration here. So given an arbitrary D on BC and draw a parallel line through D parallel to AC and do the same thing. You draw a parallel line about AB passing D as well. And you move the D on BC and connect the diagonal. You probably won't see anything special about the diagonals, but if I have a history of all the points that I sweep, then I have a very nice parabola as an envelope bounded by all the tangent lines. And F is the focus point, and this parabola is called Artzt parabola. Okay, let's see how to construct this point or this trajectory inside the Wolfram language directly, or maybe indirectly. First, let's introduce a very important idea in solving triangle conics in general. It's called barycentric coordinates. The barycentric coordinate is a very powerful tool in doing all kinds of triangle conics and some special points. What is usually requires is you convert any point inside into triangle, for example, K and F, as a weighted sum of ABC. ABC is the vertices, and lambda 1 plus lambda 2 plus lambda 3 equal to 1. Why it's called a projective space is I really do not care the absolute value of lambda 1, lambda 2, lambda 3 in general. But if I have coordinates called a lambda 1, lambda 2, lambda 3, it's the same thing as a 2 lambda 1, 2 lambda 2, and 2 lambda 3. And we can always normalize their sum to 1. So think about it's lambda 1 is lambda 1 over lambda 1 plus 2 plus lambda plus lambda 3. So we can always normalize the coefficient with sum to 1. And there is a built-in function in a Wolfram language function repository is if you give it specify 3 coordinates of ABCs respectively, and one coordinate, so for example for K inside this diagram, and you can convert the point of K as lambda 1, lambda 2, lambda 3. And if you have lambda 1, lambda 2, lambda 3, you can convert it back using these formulas. So this is basically the idea about barycentric coordinate. But when is it useful is if we do have something invariant. So say in this case, I can change lambda and change the point A, and every time I change the shape of the triangle, the parabola also changes, okay? But there is one thing that's probably not changed, but you won't see that in this plane. We have to convert it back into the lambda 1, lambda 2, lambda 3 plane, okay? Which is called a projective triangle plane. So in this case, the first step is we do need to check something, some cases that it's convenient for us to use barycentric coordinate. So here is a very simple demo. I put a manipulate function here. So manipulate is outside controllers. You can control 2 variables. One is v3, the other is a pick. I will show you the example here. So as you move the triangle, of course the point here is the centroid. If you remember what is the centroid, it's the incidence of 3 medians. So you see, if you elongate this line, it will hit the midpoint of this line. Same thing as elongation of this particular line, and it will hit the middle point of this line. Okay, so the incidence is called centroid. So if I move the point the triangle around this point changes. But if I convert it into barycentric coordinates, it is invariant. You see, it's 0.3, 0.3, 0.3 here, okay? But it's not applied to every point. If we change the centroid into the incenter of the point, for example, it will actually change. Okay, it's variant in the projective space. But for incenter, there's another one that also works. It's called a trilinear coordinate. For trilinear coordinate, it's the barycentric coordinate divided by the length of each side respectively, and you will have something invariant for incenter as well. You can see the 0.3, so 1/3 is invariant for the incenter. So what does the barycentric coordinate comes from? It comes from the ratio, so the ratio between subtriangles inside a reference triangle, and all the subtriangles shares the same vertex. For example, in the centroid case, I have 3 triangles, 1, 2, 3. They all share the same vertex here, and the barycentric coordinate is simply the ratio between, you can assume the ratio of that guy is 1, and this may be x, and this is y. So 1 plus x plus y should be 1 if it's normalized. And in the case of centroid, all areas are the same. These 3 triangles share the same area. And because they are share the same area, so each one is 1/3. That's why you can see the coordinate is 1/3, 1/3, 1/3. Okay, it's invariant under this transformation. Okay. The idea of invariance in projective space can be generalized into a curve. So it's not only limited to the points we have seen. If you know the Kimberley triangle-centered Wikipedia, they have millions of points in the context, and you can find a lot of them are just like centroid, invariant under barycentric coordinate transformation. And this is also sometimes works for the curves, and especially for these conic curves or the curves with degree 2. So if you play with the example, and you can see these parabola actually tangents to both AB and AC. And it's not only 2 tangent points, we also have a 3rd tangent point. This is exactly the medial line. You take a medial line, which means AE equal to EB, AF equal to FC, and K is exactly the midpoint of E and F. So this is actually you tangent 3 points, okay, or 3 lines. But in general, this type of curve is called bitangent family. We only require that it's tangent to AB and tangent to AC, and we can specify the tangent point in general case. So how can we do that? Let's do an experiment. The first, define tangent line first, number 1, and the second tangent line. And xy is in projective space. And fxy is a function of xy. You can, if you're not familiar with Wolfram languages, this means the first argument, second argument, and the set delay. So this function will not evaluate until I put something inside fxy. Same thing for the g. And what we can do here is the general function for these bitangent family can be specified as alpha times f and g. F and g are the specified tangent line, and 1 minus alpha times another line. So to simplify the problem, I specify the line as this vertical line. So vertical line is x equal to 1, x equal to 2, and anything. So t is a variable that can change from 1 to 3. And alpha is a parameter. This parameter changes the specified shape of the bitangent family. It's whether ellipse, circle, parabola, or hyperbola. So it's a parameter that changes the shape of the conics. And the t is also variable. T specify the tangent point of this conic and the two tangent line. You can make alpha small and to see it's the tangent line, exact location of the tangent point. And if you make alpha a little bit larger, then it's close to the hyperbola, and it's actually tangent to this line, but it's not very clear. Okay, and at some point we do have a parabola. So we can change the position of t. So it's like change the tangent point of this parabola. So it can miss B and C, but we can also give it a proper t, so that B at the tangent point exactly at B and C. So if you do some computation, for example, in this case, you can specify which tangent line F and G are, and also specify where the tangent points are. Oh, in the parametric or barycentric plane, or the projective plane, these points have special meanings. So everything inside is alpha, beta, gamma. So 2 times alpha, 2 times beta, 2 times gamma are the same. It's irrelevant about the multipliers of the coordinates. It's only about the ratio is among these 3 coordinates. So B is something like 1, 0, 0, or 0, 1, 0, or 0, 0, 1, based on your choice of the barycentric coordinate. So if we specify A as a point, and we looking for this line, then the projective coordinate is y times z minus 1/4 x squared equal to 0. So this is the formula that we use to generate this line, this curve. So you can it's quite a simple exercise for you guys to try coordinate computation to get this formula. The shape of the parabola is this. It's invariant of A. So regardless how you change the A, in the projective space, this parabola is fixed. It's just like the centroid in the first example we see. So you change the point of A, the barycentric coordinate for the centroid won't change. So the next step is, if we know some of the point on this curve, we can actually reconstruct this curve using this information. This is so good because no matter what kind of shape we have, so once we have found some point on the curve here, we can use this formula to convert it back into some point on this curve. And we use a function called 5-point conic inside the Wolfram language function repository. I'll show you later. And let's take a look at this parabola. If you run that, this also it's a function repository function. It gives you the exact location. If you want to take a look at the implementation of that, you can just go to the function repository page, or just hover a mouse over there and click the book sign here. So we have equation here, and the focus point, which is marked here. Vertex, I did not mark, but should be somewhere here. And the directory X is the line from which all the points share the same distance between this guy and the direct somewhere on the line. We can put directrix back into the plot we have here. So what I mean is that the point on the parabola, if we find the distance between, say, this point to this point, and its distance between this point and this line, they're all the same. So this follows the definition of parabola, if you know the geometric or optical means of that. Oh, let's move on, and you can read the other information about how this parabola deviates from the canonic form. Usually means either the symmetry axis of symmetry is parallel to the x-axis or the y-axis. Okay. Let's move on to the reconstruction part. Say we have this parabola. Okay. So how do we find this exact envelope in the real plane? Okay, what we do, we can either do it symbolically using a formula on Wikipedia. Also, we can do that just numerically. If we don't have the 5-point conic function, I probably will show you how to do that symbolically, but that function just makes me really lazy to do the formula conversion part. So what you can do is, for example, we choose 5 points on this curve. So subdivide means I divide this 0.05 to 0.8 in 4 divisions, equal distance. You know, if we divide into say 1 division, then we have 2 endpoints. If we divide into 2 sections, then we have 3 endpoints, including the middle one, of course. So in general, if we divide into n pieces, we should have n plus 1 points. So this is exactly the idea behind it. Say I have 5 points from 0.05 to 0.8, which means I choose 5 points along the vertical lines using the coordinate of y. And you can see that these points are color labeled. So 1, 2, 3, 4, 5 points using the color information, because I really need to show you what's the correspondence between the points on this line and the points on this real plane. Okay, and this is simply, if you know a y, you can solve it uniquely about x. If I choose x is some point between 0 and 1. So I just give it any random initial guess. This is a kind of valid initial guess for you. And if I choose y equal to 0.05, then the x should be somewhere like 0.35. As we can take a look. This is a point is 0.3 and this is 0.305. So it's good. This is close. So this is way better than choosing x, because you can see if I choose x here, it usually have 2 y's. So for find root I, in this case, I prefer to choose y and solve for x so that I can always have a unique x. I don't have to worry about the branch cut for multi-valued functions here, right? And I can just solve for all the points on this line, because I know x and I know y, and the z, according to the definition of this parametric curve, it's lambda 1, lambda 2, and the 3 is 1 minus lambda 1 plus minus lambda 2. So this is really valid. And you can, once we have that, we directly solve for the value of z. So this is a very straightforward way to compute. And this is guaranteed that x plus y will not exceed 1. Because in the projective plane, x plus y equal to 1 is this line. So anything under this line will not be exceeding this sum, right? If you draw any line here, it's the intersection of, say, 0.8 to this 0.8. It's a line parallel to 1, 1 here. So any point on that corresponds to sort of line with the sum equal to a number less than 1. Okay, so this basically gives us all the points that we can choose from that, and in turn we have these points in the projective space. Now let's move to the next part. Is somewhere this triangle, once I set it, it actually looks like this triangle in this configuration. And after the first step, we find all the projective space points in the projective space. We convert them back into the real space. What we can do is, using the formula here, it's weighted sum of ABC. This is the same thing. The try2 is the second triangle, try2 here. And each V is one of the projective points. So one of this, one of this, one of this, one of this, in total 5. And once we have all the points in the real space, and we can use this function to directly compute the explicit formula or implicit formula for x and y to describe this parabola. So this is the curve we have here. And to plot this curve, simply using contour plot. So this equation equal to 0, and specify x equal to -1 to 1, y is 0, 2. So this is a triangle roughly look like this in the coordinates in the space. I use slightly different coordinate system for this original demonstration and the second one, but the overall computation will not be too off here. And okay, then you use contour plot to plot this line over the space here, and I can compare with the points in the projective space and the lines in this case. Okay, and you can see this curve actually indeed is touching the triangle at the left corner and the right corner. So these two corresponds to this corner and this corner. So this is well, they kind of looks a little similar, but in general their shape or the size is quite irrelevant. This triangle can be gigantic, enormous, but does not change in these two cases is, first thing, the curve is always parabola in both cases. The second thing that or third thing they don't change is they touch the point in -1, 0 and 1, 0 in this case. So this is the bitangent part of the bitangent family. And let's go back to the example here. You can see if I specify t in the two lines here, then the parabola is definitely fixed. So this concludes our reconstruction part for this point inside real plane from the projective space. Thank you for listening. See you next time.